Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today's topic is the pendulums. Objectives are: no simple pendulum occurs in any system in which there is a restoring force such as F s equals negative kx. Understand with a small angular displacement, the oscillations of simple pendulum, physical pendulum, and torsion pendulum are simple harmonic motion. Be able to derive the expression for the period of simple harmonic motion for simple pendulum, physical pendulum, and the torsion pendulum. First, let's consider simple pendulum. A simple pendulum is an idealized model consisting of point mass suspended by massless, un-stretchable string. When the point mass is put to one side of its straight down equilibrium position and released, it oscillates about its equilibrium position. So the simple pendulum oscillates due to restoring torque. What is the torque? Torque equals R cross F. R is the distance between the action of the force point to the axis rotation point. So in this case, R equals to L. F in this case is mg. So torque equals negative L mg sine theta. Negative means when the theta is positive, torque is negative. They are always in the opposite direction because the torque is restoring torque. When theta is very small, sine theta is approximately equals to theta. That gives us torque equals negative L times mg times theta. So compare this with Fx equals negative kx. We know this is simple harmonic motion. That's how we know this simple pendulum is simple harmonic motion when the angle is small. Using Newton's second law, torque equals I alpha. I is mr squared in this case. R equals L, so I equals ml squared. Substitute into torque equals I alpha. You can solve for alpha. Compare this with ax equals negative omega squared times x. You can see omega equals to this. And so t is 2 pi square root of L over g. This is the period of a simple pendulum. So simple pendulum is vibrating with small angle is described by the function theta equals to capital theta times cosine omega t plus v, where capital theta is the angular amplitude because it's a simple harmonic motion. Example, a simple pendulum has a period of 2 seconds for small amplitude oscillation. What is the length of the pendulum? If we know t equals to 2 pi L over g, we can solve for L. So there is a trick here. Pi and the square root of g are about the same, so these two can cancel. Approximately t equals to 2 times square root of L. So L equals to t squared over 4. In this case, it's just 1. Which of the following equation could represent angle theta that the pendulum makes with vertical as a function of time? We know this simple harmonic motion, so that's sinusoidal function. This sine has to be omega t. So what is omega? We know omega equals 2 pi over t, so omega equals to pi, so the answer has to be B. Now, when a body oscillating on a horizontal spring passes through its equilibrium position, the acceleration is 0. When the bob of an oscillating simple pendulum passes through its equilibrium position, is its acceleration 0? And the answer is no. Why is it? Because at that point it's still moving, it's changing directions. There is a centripetal net force, which is a combination of tension and gravity. You'll have a net force going toward the center. So therefore, if net force is not 0, acceleration is not 0. The motion of physical pendulum is simple harmonic motion. So a physical pendulum is any real pendulum that uses an extended body in motion. Unlike a simple pendulum, all the mass is concentrated at end. Physical pendulum the mass is distributed throughout. So the oscillation of physical pendulum is caused by restoring torque. So here is the irregular shaped body oscillating about point O is a physical pendulum. So let's take a look at a torque. Torque equals R cross F. R in this case, that equals negative RF sine theta, because it's negative because torque and angular displacement are in the opposite direction. R equals to D, F equals to mg, so when theta equals to small, When theta is small, sine theta is almost theta. That gives us torque equals negative d mg times theta. So compare this with fx equals negative kx. We know for small angle, the oscillation of physical pendulum is simple harmonic motion. We can find a period. To find period, we have to use Newton's second law, torque equals I alpha. And by the way, I is I center of the mass plus md squared. This is parallel axis theorem. So torque equals I alpha. We solve for alpha. From here, we can find omega. That's how we find period. Do not try to memorize. I don't want it to get confused, but you really should be able to derive this from torque equals R cross F, then using Newton's second law to find omega. So again, the motion of physical pendulum vibrating with small angle is described by the same function, that's sinusoidal function, theta equals to capital theta cosine omega t plus phi. This capital theta is the angular amplitude, that's maximum of the angular displacement. Take a look at this example. Uniform rod with length L pivoted at one end vibrate through small angle. Find a period of its motion and compare it with simple pendulum of the same mass and length. How do the two compare? So to find a period of this physical pendulum, remember we have to start with torque. Torque equals to R cross F, mg, L over 2 sine theta, L over 2, because here it has to be from the center of the mass to the axis rotation. So this is when theta equals is small. This is the torque. Torque equals I alpha. What is I? I for the bar is 1/3 ml squared. Set the two equals to each other. You can solve for alpha. From here you can find omega. You can find t. Compare this with simple pendulum. So you can see t is smaller. So the uniform rod with same mass and the same length as the simple pendulum will have a shorter period. Let's take a look at another question. The center of gravity of simple pendulum mass m and length L is located at the position of a pendulum bob, a distance L from the pivot point, just like this. The center of gravity of a uniform rod of the same mass m and length 2L pivoted at one end is also distance L from the pivot point. So this is the center of the mass, is also distance L from pivot point. How does the period of this uniform rod compare with this simple pendulum? So for simple pendulum, this is this. What is the, how do we figure out the period of this rod? First, let's go with the torque. Torque equals mg L sine theta. When theta equals to small, it's just mgl times the theta, and torque equals to I alpha. I is 1/3 ml squared, but the whole length is 2L. Substitute into I equals to I alpha. You can solve for alpha. From here you can solve for omega, solve for t. Compare these two t's. As you can see, this period is bigger than that. So the period for the physical pendulum with length 2L and mass m, its period is longer. Now let's consider the motion of a torsion pendulum, which is also a simple harmonic motion. For torsion pendulum, watches keep time based on regular oscillations of a balanced wheel initially set in motion by a spring. The wheel has a moment of inertia I about its axis. A coil spring exerts a restoring torque that is proportional to the angular displacement theta from the equilibrium position. Torque equals negative kappa theta, where kappa is a constant called torsion constant. So torque equals to I alpha equals negative kappa theta. From here we can solve for alpha. From there we can find omega, we can find t. So again, the displacement equation is the same, just like the simple pendulum and physical pendulum. Theta is capital theta cosine omega t plus phi. This capital theta is the angular amplitude or maximum angular displacement. Let's take a look at this example. So torsion pendulum show consisting of a disk of rotational inertia I suspended by flexible rod attached to a rigid support When the disc is twisted through small angle theta, the twisted rod exerts a restoring torque that is proportional to the angular displacement. Torque equals negative beta times theta, where beta is constant. The motion of a torsion pendulum is analogous to the motion of a mass oscillating on a spring. So in terms of quantities given above, right? But do not solve differential equation. You need to write the differential equation that could be used to determine the displacement theta of the torsion pendulum. So you start from torque equals to negative beta theta. We know torque equals to I alpha, that's Newton's second law. Set the two equals to each other. What is alpha? For differential equation, alpha is double derivative of theta t relative to t. So it's I d squared theta over dt squared equals negative beta theta. This is differential equation. Now we're going to using the analogy of a mass oscillating on a spring. You need to determine the period of torsion pendulum in terms of the given quantities and functional and fundamental constants. So again, solve for alpha. From alpha you can solve for omega. From omega you can find t, and that is t. Another example, you are given a non-uniform thin rod of mass m, length L, with pivot attached to one end. The center of mass is located, center of mass right over here, a known distance d from one end with a pivot right over here. How do you determine I rod from a pivot with minimum error? So we know physical pendulum. We can set this as a physical pendulum. We can set the rod as a physical pendulum. Once we set it as a physical pendulum, what we can do, we can measure the period. Then we can use the relationship between the period, mass, dg, and I rod. From there, we can determine I rod. So first, we set this as physical pendulum. So how do we find t from this physical pendulum? Remember, first step, you have to find the torque. Then you use Newton's second law. That's how you find omega and t. So here's a torque mgd sine theta. When theta is small, this becomes negative mgd times theta. Set torque equals I alpha, Newton's second law. You solve for alpha. From here, you can solve for t. So this is t. So what we can do is, we can measure this t. How do we measure t? So suppose we can determine, if we can determine t, then we can use this equation, right, to solve for I rod. How do we determine t though? To determine t, we lift the rod at a small angle and let it oscillate. We use stopwatch to measure the time t, but to minimize the error, we need to measure the t of 10 oscillations. Then the period is little t, lowercase t, divided by 10. Once we determine t, we can use this equation to find I rod. Sometimes this center of mass is not given to you. Suppose that's not given to you. If we were not given the location of center of the mass of the rod, how can we determine it? We can determine the center of the mass by placing a rod on a fulcrum. Just basically try to balance it. The center of mass is a point above the pivot fulcrum when the rod balances, right? Or you can push the rod at the edge of the table until it's just start to tip over. So the point above the edge of the table, that is the center of the mass. And that's it for today. Thanks for watching.